In this video, I want you to get some experience working with story problems or word problems involving permutations as well as combinations. So we're going to go through these together, and as we go through them, I want to talk about some of the different formulas as well as some of the different definitions. We're going to be working with permutations, combinations, factorials, probability in a few of the problems, as well as the fundamental counting principle. So let's dive into the first problem, and we'll kind of explain this as we go through it. For the first one, it says, how many ways can you arrange all the letters in the word math? So what do you think for that problem? Well, there's a couple different ways to do this problem. One way to do it is to use the fundamental counting principle. And what you would do is you would diagram this out. You'd say, there's 4 letters. How many choices are there for the first letter? So imagine if you were picking these letters out of a bag. Well, there would be 4 choices, right? And then once you pick one of the letters, there's going to be 3 left. So you're going to have 3 possibilities for that second letter that you pick for the word. 2 and then 1. And if you multiply those together, you're going to get 24 different so-called words involving the 4 letters in math. Now notice there's no letters repeated, and we'll talk about some of the problems later on where there's repetitions of a particular letter. But for this one, it's just going to be 4 times 3 times 2 times 1, and this is the fundamental counting principle. You just see how many choices in each category and you multiply them together. The other way to do this is to use this permutations formula here, and what you could do is you could say out of 4 objects you're picking, like P for picking or permutations, 4P4. You're picking 4 out of 4. And so if we put this into the formula here, you can see that this number that comes in front is our n. That's going to be 4 factorial over 4 minus r, which r is 4, so that's 4 minus 4 factorial. So this comes out to 4 factorial over 0 factorial, and you want to memorize that 0 factorial is actually 1, but with 4 factorial is you start at 4 and you multiply consecutively down to 1. So this would be 4 times 3 times 2 times 1, all divided by 1, which is the same thing we got here, 24. So 2 different ways to look at that one. For number 2, it's very similar to number 1. It says, how many ways can you arrange just 2 of the letters in the word math? Okay, what do you think for this one? A couple different ways to do this as well. You could use the fundamental counting principle. You could say there's 4 choices for the first letter. Once you pick that letter, right, how many choices are there for the second letter? There's only 3, so 4 times 3 is 12. The other way to do that is to use this permutation formula here. Out of n objects, how many ways are there to pick r objects where the order matters, okay? So the order is important with permutations, not with combinations. So for example, this one would be 4p2, which is 4 factorial over 4 minus 2 factorial. So that's going to be 2 factorial in the denominator, 4 factorial in the numerator. And if we expand this out, 4 times 3 times 2 times 1 over 2 factorial, which is 2 times 1, you can see that these are canceling, and we just get 4 times 3, which is equal to 12, the same thing we got here. So either the fundamental counting principle will work, or using this NPR formula will work as well. Okay, for number 3 now, let's try this one. It says 8 runners are running in a race. In how many ways can a gold, silver, and bronze medal be awarded? So what do you think for that one? So the question you always want to ask yourself in these problems is it a permutation? Is it a combination? Does the order matter, or does the order not matter? Well, say for example, runners A, B, and C versus like C, B, and A. So here you'd see A gets the gold medal, whereas here C is getting the gold medal. Same 3 people are finishing in the top 3 places, but it's a different awarding of medals. So this would be definitely a permutation. And what we can do is we can say out of 8 runners, you're picking 3, okay, or 8 permutation 3, which is equal to 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. And if you expand this out, you get 8 times 7 times 6 times 5, all the way down to 1. And 5 factorial is 5 times 4 times 3, all the way down to 1. So these are going to cancel all the way down. It's just going to be 8 times 7 times 6, which makes sense because if we were to use the fundamental counting principle here, we say how many ways are there to award like a gold medal? Well, out of 8 runners, there's going to be 8 ways to do that. But once you award that gold medal, there's only 7 runners left to win that silver medal, right? 7, and then 6 left for the bronze. So 8 times 7 times 6, you can see we're getting the exact same result. And just to, in case you're doing this on your own, let's get an answer here. That's 336 different ways or outcomes. So we haven't gotten into any probability problems yet, but here we're just talking about the number of possible outcomes. Okay, number 4, see if you can do this one. We've got 20 basketball players form teams of 5 players in each team, right? Each player can play any position. How many teams of 5 can be formed? So what do you think for this one? When you form these teams of 5 people, does the order matter? Well, in this case, because every player can play every other position, the order doesn't really matter. We're just looking at that particular group of 5 people. So when the order doesn't matter, we're thinking combinations, okay? And in this case, you can see out of the 20 players, we want to choose 5 of them where the order doesn't matter. So it's 20 combination 5, which if you use the formula here, it's going to be 20 factorial over 20 minus 5 factorial. 5 factorial. Now notice this R value right here. See, the R value is, this is the only thing that's different between the permutation formula and the combination formula. And what this R factorial is doing is it's dividing out all the multiples, all the multiplicities you could say. So 5 factorial, there's really 5 times 4 times 3 times 2 times 1. There's 120 different ways of arranging 5 players. But they're all going to be on the same team, so you only count that team once, not 120 times. So that's why we're dividing out these multiplicities here. So if we simplify this further, this is going to be 20 factorial over 15 factorial times 5 factorial. And you don't want to make the mistake of saying, oh, this is like 75 factorial, or 20 divided by 5, that's 4 factorial. It doesn't work that way. You have to actually expand this out. 20 times 19 times 18 times 17, etc. Or you can use this combination key on your calculator. It's under the probability menu. So I'm going to do 20 math probability, go down to the combination. So 20C5, and this is coming out to 15,504. 15,504 different ways that you could form these 5 player teams out of 20 basketball players. Okay, so for number 5, a little different problem here. The letters A, B, C, T, U, and V are all placed in a hat, okay? Find the probability that you draw exactly 3 letters and you can spell the word cat. Okay, so now we're transitioning a little bit to talking about probability. And so the definition of probability is the number of successes, meaning the number of things that you want, divided by the total possible outcomes. Okay, so it's like if you were to spin a spinner and you say, what's the probability I land on an odd number? 1, 2, 3, 4. Well, there's 2 odd out of 4 possible, so it'd be 2 over 4, which is 1/2. That's your probability. So it's what you want, or successes out of the total. So in this case, what do we want? Well, we want the letters C, A, and T, right? So we're basically saying out of those 3 letters that we want, how many ways are there to choose all 3? And out of not 20 letters, but 6 letters, how many ways are there of choosing 3 letters? So this gives us the total possible of outcomes, or the ways of choosing 3 letters, where the order is not important. Because when you get these letters in your hand, you can arrange them any way you want. So we don't want to count them, the ordering is different. We want to just count it as one group of 3 letters out of 6. And so 3C3 is going to equal 1. And 6C3, let's see what that comes out to. 6 combination 3 is 20, so you have a 1/20th chance of being able to do this. Now, this kind of makes sense because out of 3, how many ways are there choosing all 3? Well, there's only going to be one way of doing that, or you could say, you know, there's only going to be one way of getting the success of drawing these 3 letters cat, right, out of the 20 different ways of drawing 3 letters out of the 6. So different ways to think about it, but combinations because the order doesn't matter, probability because we're trying to figure out the chance that this occurs. Number 6 here, it says, at a party with 30 people, if each person shakes hands with every person, how many total handshakes take place? Okay, this is kind of a common problem, but imagine you're at a party and you're trying to shake everybody's hand. See, the thing is, when 2 people shake hands, how many handshakes is that? Well, it's just 1, right? So you don't want to double count. And so what we're thinking here is we're thinking of out of 30, how many ways are there choosing 2? Okay, so 30C2. So A and B, B and A, that's the same 1 handshake. So that's why we're not treating it like a permutation, but rather a combination. And 30C2 is going to be 30 factorial over 30 minus 2, which is 28 factorial, times 2 factorial. So let's go ahead and do that on the calculator. That's, let's see, 30 math C2. All right, so that's 435 handshakes. Okay, number 7, let's see if you can do this one. It says you and 3 friends are running for a 4-person committee. 100 people are running. What is the probability that you and your 3 friends win the 4 seats? Okay, so interesting question. So the first thing is, we're trying to basically figure out that you and your 3 friends, that's 4 people, win the 4 seats. There's only going to be one way that that can happen, or you could think of this as out of the 4 people that you want to win, you know, that you're a group of 4, how many ways are there of choosing all 4? So that's only going to be one way. But then out of 100 people, how many ways are there to choose 4 for this committee? Now, how do I know that it's combinations and not permutations? Well, when you're talking about a committee, it's not like there's a president, vice president, secretary, treasurer. All the positions are basically the same. So when you interchange the ordering, it doesn't really matter. It's the same committee. So you don't want to count those as separate outcomes. That's why we're using combinations. So here we said 4C4. There's only going to be one way that you and your 3 friends win. And then how many ways are there of choosing 4 out of 100? Let's see what 100C4 is. Combination 4. That's a big number here. We have 3, 9, 2, 1, 2, 2, 5. So 1 out of about almost 4 million. Okay, so slim chance, right? Number 8 now, it says, what is the probability that in a standard deck of cards you are dealt a 5-card hand that's all diamonds? Okay, so you have to be familiar with cards to do this problem, but you want to be dealt a 5-card hand that's all diamonds. So in this case, we're thinking about probability. What's the number of successes? Well, out of the 13 diamonds, how many ways they're choosing 5? So when you do the combinations, this is how many are in that group of what you want, the 13 diamonds, but you're trying to choose 5 out of that 13. So how many ways could that occur? But it's probability divided by the total number of outcomes. Well, there's 52 cards in a standard deck. How many ways are choosing 5 of those 52 cards where the order doesn't matter? So again, combinations. So let's see what that comes out to. So 13 combination 5, okay, is 1,287, and 52 combination 5 is a big number here, 259, 8960. So that's your probability, and you could reduce this down or even write it as a decimal. Okay, so for number 9, it says your teacher draws 2 names out of a hat to lead a class discussion. What is the probability that you and your best friend are chosen given that there are 30 students in your class? Okay, so again, we're just assuming in this problem that you just have one best friend, right? Not 2 or 3, okay? But it says, what's the probability that the 2 names drawn are going to be you and your friend? Well, again, there's only one way that it could occur, or if you want, you could think out of these 2 people that you want, you and your best friend, how many ways they're choosing those 2. So 2C2 or 2 combination 2, which is 1. But then how many ways are there of choosing 2 students out of the 30? That's going to be 30C2. Again, we're using combinations because the order doesn't matter. It's not like it's a president, vice president, etc. So let's see what that comes out to. That's 435. So it's a 1 in 435. Okay, so I'm trying to give you a good sampling of all these different types of problems that come up when you're working with permutations, combinations, probability, etc. So number 10 is a little bit different. It says, how many distinct ways can all the letters in the word geometry be arranged to form a new word? So we're using all the letters, and we're making a new quote-unquote word. It might not actually be a word. It's just kind of, we're calling it a word. So the first thing we want to figure out is how many letters are there? There's 1, 2, 3, 4, 5, 6, 7, 8 letters. So when you arrange 8 items, how many ways are there to do that? Well, that's going to be n factorial or 8 factorial. You could say, well, there's 8 choices for the first letter, and then 7 choices for the second letter, and it's 6 for the, it's like you're picking a letter out of a bag and there's 8 letters, so all the way down to 1. So we could say this is 8 factorial. But we have a different situation here from the first problem we did where we talked about the word math. Here you can see there's actually 2 E's. Okay, so if I was to take this E and like interchange them, it would still look like the word geometry. It wouldn't be distinct, it wouldn't be unique, it wouldn't be different, right? So we don't want to double count, when I switch these 2 E's. So to avoid double counting, what we have to do is we have to divide by 2 factorial. Now 2 factorial is just 2 times 1 is just 2 because there's 2 different ways. If there was 3 E's, we would divide by 3 factorial, which is 3 times 2 times 1, which is 6. There would be 6 different ways that you could arrange those like 3 E's but it would still look like the same word. But in this case, there's just two e's, so we're dividing by 2 factorial. And let's expand this out. So this would be, let's see, 8 times 7 times 6 times 5, all the way down to 1, divided by 2 times 1. And let's see what that comes out to. So 8 factorial divided by 2 factorial. So it comes out to 20160. So 20,160 ways that you could do that. A common example with this one that often comes up is like the word Mississippi. So Mississippi, actually, there's 11 letters. That's 11 factorial. But there's 4 S's, there's 4 I's, and there's 2 P's. So you'd have to divide by 4 factorial, 4 factorial, 2 factorial to divide out those multiplicities. Okay, so let's look at number 11 now. It says how many 4-digit numbers less than 7,000 can be formed such that the number is odd. Okay, so what I like to do sometimes with these problems is I like to diagram it out. Okay, it's a 4-digit number, and it has to be less than 7,000. So the first digit has to be what? It has to be a 1, 2, 3, 4, 5, or a 6. It couldn't be a 7 because then it wouldn't be less than 7,000. So that means there's 6 choices for this first number. Now notice I didn't mention 0 because if it was 0, then it would only be a 3-digit number. Let's jump to this last number here. If we want it to be odd, the only way it can be an odd number is if the last digit is odd. It has to be a 1, 3, 5, 7, 9, right? So there's 5 different outcomes for the last digit. But these 2 middle digits, they could be 0, 1, 2, 3, 4, 5, all the way up to 9. So 0 through 9, if you add those up, there's actually 10 possibilities for the second digit and 10 for the third. So if you multiply these together, you're going to get 6 times 5 is 30 times 100, which comes out to 3,000. Which you probably could just figure that out, just on your own. You could say, well, from 1,000 to 7,000, that's 6,000 numbers. Half of them are odd, 3,000. But sometimes the problems are a little bit more complicated, so I wanted to show you this process of using this fundamental counting principle. Okay, for number 12 now, it says, in how many ways can a 10-question true-false exam be answered, assuming that all questions are answered? This is also a common problem that comes up. Again, if it's a 10-question exam, imagine those 10 questions. How many ways can you answer that first question? 2 ways, right? Either true or false. How many ways can you answer the second question? 2 ways, right? True or false. How many ways can you answer the third question? 2 ways, true or false. So what's 2 times 2 times 2 times 2 10 times? Well, that's going to be 2 to the 10th, which is equal to 1,024 different ways that you could answer this true-false test. Okay, if there's a problem that you have a question about regarding permutations, combinations, or probability problem involving permutations and combinations that we haven't covered yet in this lesson, go ahead and put it in the comments below. And if you're watching this video, see if you can answer those questions that people are posing down there in the comments questions, in the comments. So for number 13 now, it says, in how many ways can 5 people stand in a circle? Now, this is a little bit more complicated problem than if we say how many different ways can 5 people stand in a row. See, if it was in a row, it would be like this. They could stand 5 choices for who stands here furthest to the left. Once that person stands there, there's 4 people to compete for who's going to stand right here, and then 3, and then 2, and then 1. And you would multiply all those together, and you'd say there's 120 different ways. The problem here, though, is that when you're standing in a circle, okay, kind of imagine my 5 fingers here, it's like a dial or a knob. Like if I was to rotate like that, right? The thing is you can turn that knob 5 times, right, until you get back to the original position. But whoever's standing on your left and who's ever standing on your right, when you keep turning like this, you're going to be in the same relative position to one another. So what you have to do is you have to divide by 5. So if you wanted a formula, this would look like n factorial divided by n. So in this case, there would be 24 different ways it can happen. Now, when you're doing these problems with some of these larger numbers, it gets a little bit abstract. And what I recommend is to pose a simpler question. Maybe say, for example, the people are like this, A, B, and C, right? Well, there's 3 people. That would be 3 factorial, which is 3 times 2 times 1. There's 6 ways of ordering them in a row. But imagine if it was in a circle now, like A, B, and C. Not much of a circle with 3 people. But you can see that, like, so you can turn it like this, 1, 2, you know what I mean? You can rotate it. So that's the idea here on this problem. So let's look at number 14 here. It says, in a shipment of 10 items where 3 are defective, in how many ways can you receive 4 items where 2 are defective? Okay, so this one's a little bit challenging in the sense that there's 10 items, 3 are defective. I'm just going to say 3 are bad. So that means that 7 are good. So let's say 7 good, 3 are bad, but you're trying to receive the shipment where you're going to get 4 items, right? You want to find out how many ways there are to get 2 defective or 2 bad. That means that 2 are good. So the way this would happen is there's out of the 7 good, how many ways are there to choose 2 times out of the 3 bad, how many ways are there to choose 2 of those 3 bad ones? And then you're going to multiply these together. So again, remember that first number. That's how many are in that group. 7 good. Here, how many ways are there to choose 2 out of 7 where the order doesn't matter? It's not important. And out of the 3 bad ones, how many ways are there to choose 2 where the order is not important? So let's go ahead and multiply those together. So we have 7 choose 2. Let's see here. 7 choose 2, which is 21. And 3 choose 2, which is 3. So that means there would be 63 different ways that that could occur. If you want to see more examples as well as more of an detailed description of all of the permutations, combinations, factorials, fundamental counting principle, probability, follow me over to this video that I did earlier here, and we'll go through some more examples together.